A lot of people are, their power's out. Okay, so we're just going to find, we're going to find the cube roots of 1 plus I. So the way we're going to do this is first you're going to have to turn this guy into something into polar form. Okay, polar form is the r cis theta, which is the same as r cosine theta plus I sine of theta. We have to get this into this form. So to do that, we have to find r and theta. So to find r is the magnitude of this. I'm just going to call this z. This is my z. Okay. So r is the magnitude of z. And so that is the square root of 1 plus 1, because I have 1 right there. Right? There's a 1. That's my coefficient. 1 plus 1 squared. And so this is the square root of 2. Okay. And now I still need theta. Now theta is the argument of z, and that is the arctangent of the imaginary part all over the real part. And so in this case, it's 1 over 1. And the arctangent of 1, well, when is the slope equal to 1? Well, that happens here at pi over 4 and negative pi over 4. I'm sorry, strike that. 5 pi over 4. But this one has a positive x and a positive y, and this one has a negative x and a negative y. So this is the one I want. And I know that it's a positive and a positive because they're both positive. Okay? I have a positive real and I have a positive imaginary. So my theta is pi over 4. So now what I do is I write out a nice little equation. Z cubed is equal to 1 plus I. That's what we're trying to find. That's the problem that we're being asked. Okay. Find me the z's such that when I cube it, it equals 1 plus I. Okay. Now, I have my r and my theta for this, so I'm turning this into this form. And so that is the square root of 2 times the cosine pi over 4 plus I sine of pi over 4. Now, I want z alone, so I have to cube root both sides. And if it's okay with you guys, I'm just going to leave this as 2 to the 1/2, just for, simple.
What about the other two rotations around?
I haven't gotten there yet. Okay, now, as Rivik was pointing out, what I need is, I need 3 answers. Okay, I need 3 solutions. So what I'm going to do is I'm going to find 2 more angles, 2 more cycles in order to get all 3 answers. And each cycle is going to be another wrap around the unit circle. Okay. So, those are your coterminal angles, angles that have the same value. They're just 360 or 2 pi down the road. So I have pi over 4 plus 2 pi, get a common denominator. And so I have 9 pi over 4 is my next answer. And I'm just going to go ahead and say that I've got these 3 answers. 2 to the 1/2 cosine of 9 pi over 4 plus I sine of 9 pi over 4. All right, to the 1/3. And yeah, right there. Parentheses. Yeah, okay, good. And now I need another cycle because I need 3 cycles altogether. This is the very first one. 1 cycle, now another cycle. And now adding another 8 pi over 4 onto that gives me 17 pi over 4. And now to finish the problem, I use de Moivre's theorem. Well, first of all, I apply the 1/3 to both things inside. One of them is this R, which is my radius, and the other one, which is the pair of parentheses that contains my formula, not my formula, my complex number. And so my final honest to God answers are 2 to the 1/6 cosine pi over 12 plus I sine of pi over 12, 2 to the 1/6 cosine 3 pi over 4 plus I sine 3 pi over 4, and 2 to the 1/6 cosine 17 pi over 12 plus I sine 17 pi over 12. And those are your three roots. How do we feel? Okay. Do you want to try one on your own? Okay. I'll do one that isn't too bad. Find me the, we should do the cube roots again of, let's say, -2i. And that's it. Okay. So obviously the length of this number is 2. Okay. And it's just got a purely negative component. That means the angle is -1, right? It's like when it's pointing down, straight down. So that's 3 pi over 2. Okay. It's not going left or right. I mean, if you really wanted to do it, you call this 0 minus 2i, and theta is the arc tangent of -2 over 0, which is undefined. So that means I'm dealing with pi over 2 or 3 pi over 2. And since it's negative, it's got to be the 3 pi over 2. Okay. So now, so here are my 3 complex numbers. Okay. The radius, and I just did it in cis form because it's simpler. And I found my 2 cycles. So 3 pi over 2 plus 2 pi, it gives me 4 pi more, 7 pi over 2. And then 4 pi more gives me 11 pi over 2. Now, I go ahead and apply de Moivre's. So I cube root both sides. So I get the cube roots of 2 everywhere. And now when I put that 1/3 on everybody, it turns into division. You know, it's like I get a 1/3 here, a 1/3 there, and a 1/3 there. So 7 over 2 becomes 7 over 6. 11 over 2 becomes 11 over 6. And now I pop it back out into full polar form. And the cosine of pi over 2 is 0. The sine of pi over 2 is 1. Cosine of 7 pi over 6. Okay, so 7 pi over 6 is here. My cosine is a negative square root of 3 over 2, and my y value is a -1/2. 11 pi over 6 is here. And that is it's positive square root of 3 over 2 for the cosine, and it's a -1/2 for the sine, and those are your answers. I mean, obviously, plus 0. Okay, so you got to watch your Watch your signs. Okay. All right. Yeah, just watch your unit circle. Okay, guys? You want to try one more of those, or you want to go on to something else?
What else is on the quiz?
Well, there will be, one cube root, fourth root, fifth root, something like that of a complex number. So that is going to be on the quiz. Something like it will be on the quiz. Okay.
What else? So I know.
Oh, you're just so excited. Oh, Red Vic, that's so sweet. All right. This is actually kind of a throwback to Algebra 2. I'm going to consider this the gimme problem. All right. I'm going to tell you that I have a polynomial. And its roots are -3 and 2 minus 3i. Okay. And I'm going to ask you to find the smallest polynomial that will have those roots. Now, by the way, there are different ways of doing this problem. What is one thing is, what is another root to this? Does anybody know? Just, because I have a complex root, does anybody know what the other root might be?
Positive, so 2 plus 3i. Or the conjugate.
Yeah, the complex conjugate. Because remember, when you do the quadratic formula, you get x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Well, that plus or minus gives me two answers. And if whatever the heck this is boils down to 3i, there's going to be a positive one as well, because I already have the negative here. Okay. So that's another answer. All right. So anyway, let's just keep going with it. So if these are my two roots that I know of, so x is equal to -3 and x is equal to 2 minus 3i. So now I know that x plus 3 is one of my factors. And now you want to turn this into a factor, but it can't be a factor that contains an I. So I do x minus 2, excuse me. Is equal to -3i. And then I square both sides to get rid of the imaginary number. And I get x squared minus 4x plus 4 is equal to 9. -3 squared is 9, and the I squared is -9. So now I have x squared minus 4x plus 13 is equal to 0. And so these are my two factors. Okay. And now to find the full-blown polynomial, I just multiply these two factors. 1, -4, 13, 1, 3, 39, -12, 3, 13, -4, 1. So I have x to the third minus x squared plus x plus 39. Is that cool? All right. So that's just, a throwback from Algebra 2. Hopefully, maybe, who knows? I don't know. I don't know what you learned in Algebra 2. If you learned anything in Algebra 2. Okay. Now, let's proceed. Let's do something else. Okay. So, this one's going to be interesting. I'm not quite sure how I'm going to turn it into a question, but this is interesting as well. I'm going to say, let W be a root of Z to the fifth is equal to 1. Okay. So there are two ways of solving this problem. Before I go into how to solve, before I do it myself. Think of this as a geometric series. Okay, think about this as a geometric series. That's one way to do it. The other way to do it is to turn it into cis form and actually compute it. So pretty much is like an induction step, but we're not going to go through the formal proof. But the geometric formula of it all is really the cleanest, nicest way to show it. Okay. Now, something else that might be on the test. Let's see if we can find you one that's particularly similar. Let's do this. If I told you that Z was equal to A plus 2I, A minus 3I, and I told you that the imaginary part of Z was equal to 2, find A. Now, the trick to doing this problem is first, you need to use the complex conjugate so that you actually have a real denominator. Once you've got that, find out what the imaginary part is, set it equal to 2, and solve for A. All right. And then I might ask you, find Z, like write Z.
Is that natural log of 2? I mean, Z?
No, it's the imaginary part of Z. So if you have, Z is equal to X plus YI, the imaginary part is Y. Believe me, the problems that I've crafted already work out quite beautifully. And that's why it's so hard to give you questions that are very much like it, because they're crafted problems. They're not, randomly selected. So let's do this as far as we can take it. Okay, so the real part of this is a squared minus 6 all over a squared plus 9. That's the real part. And the imaginary part is 5a all over a squared plus 9. Now, if I told you that the imaginary part was equal to 2, you would just say 5a is equal to 2a squared plus 18. And then you've got a quadratic that you would solve for a. Now, unfortunately, when you solve this quadratic for a, you wind up getting an imaginary number. And the problem is that a is already an imaginary number. Well, that's not true. Let's solve it anyway. Let's just do it for the hell of it. So 2a squared minus 5a plus 18 is equal to 0. So a is equal to 5 plus or minus the square root of 25 minus 4, a 18 all over 4, 5 plus or minus 25. And so 8 times 18 is 80 plus 64, 144 all over 4. You know, probably would have worked out beautifully if I just switched these two signs. And then it would be the square root of 13, the square root of 169, and it would have been 13. Oh, that's such a shame. It was close to a pretty answer. Oh, well. I can't make these questions up off the top of my head. Anyway, moving on. And so 18 minus 2. Yeah, all right. Well, whatever. And so now I get 5 plus or minus I square root of 119 all over 4. And that would be your A. Now, I mean, if let's just say this came out to be something nice and pretty, like the one that will happen on the test, you would then find your A, which you just did, plug it back into this thing and simplify it. And then you'd be done. Or you could plug it back into this. You already know what the imaginary part is. You don't have to fool with that. But you would take this, plug it into here, and find out what the real part is. And once you found out what the real part is, it would be, you know, z is equal to some junk plus 2i, because you already know that the imaginary part is 2. See how that works? Questions on this problem, on how you would proceed? Because I'm going to tell you that you're going to have something that looks a little bit like that, looks a little bit like that, and you're going to have to do this. Okay. What else did I pick for you? Those are going to be fun. All right. All right. If I told you that negative z squared was equal to 3 minus z, find z. So I'm going to move everything over to one side of the equation, and I get z squared minus z is equal, plus 3 is equal to 0. And now I've got a quadratic equation, and I can just say that z is equal to negative b plus or minus the square root b squared minus 4 times a times c all over 2a. And so I get 1 plus or minus the square root of 1 minus 12, or negative 11, all over 2. And so now I have 1/2 plus or minus I square root of 11 over 2. Now, the other way to solve it, which might prove useful somewhere in your future, is to say let this equal that. Just create an imaginary number, okay, and plug it in. And so now I have a plus bi squared minus a plus bi plus 3 is equal to 0. So now a squared plus 2abi minus b squared minus a minus bi plus 3 is equal to 0. So now, collecting all of my real and imaginary parts, a squared minus b squared minus a plus 3 is equal to 0. And 2abi minus bi is equal to 0i. So now b 2a minus 1 is equal to 0. So if b is 0, or a is equal to 1/2. Those are two possible scenarios. Now, if b is 0, okay, then I have a squared minus a plus 3 is equal to 0. Okay, this is if b is 0. Now, solving that quadratic equation, a is equal to 1 plus or minus the square root of 1 minus 4 times 1 times 3, which is negative 11, all over 2, which gives me back my formula again, 1/2 plus or minus I square root of 11 over 2. That gives me my answer. The other answer was if a was 1/2. If a is 1/2, then I have 1/4 minus b squared minus 1/2 plus 3 is equal to 0. So now 1/4 minus 1/2 plus 3 is 11 over 4. And that means that b is equal to the plus or minus the square root of 11 over 4. And with my a and my b together, see here, this is the real part, and the imaginary part was 0, but it would become 11 over 2, which gives me the same answer. But in here, if a plus bi is done, my real is 1/2 plus or minus the square root of 11 over 4, and b is the complex part, so it has an I on it. So I can't emphasize enough, and you should remember this as long as you are ever learning complex number problems, to equate the real and the imaginary parts together. Okay? Because you're going to have two equations and two unknowns. So this technique is quite useful. All right. All right. Last problem to try and get you ready for something would be something like And I'm just gonna change this a little bit. Cluster. Now, in a situation like this, I would definitely turn Z into this. Replace Z into your equation. Expand this whole thing out. And then you'll say that my real parts are equal to my real parts, my imaginary parts are equal to my imaginary parts. And you'll solve from there. Okay, so hopefully this was your first two steps. And now what you do is you group all the real parts. And you group all of the imaginary parts. And so now what we have is we have two equations with two unknowns. And at some point down the road in the real problem, you solve for A and B, probably by substitution or even elimination. Okay? All right. So conceptually, do you understand how to solve a problem like this? All right. So here are your techniques. Let's just simplify it down to your techniques. Equating real and imaginary parts. Another technique that's important is and then applying the Moivres. Look for quadratics. They pop up in lots of places and you have the quadratic formula. If you don't have quadratics, look for sum and difference of cubes. Know how to find R, know how to find theta. Okay. If I give you a Z, I want you to be able to graph that on an R-GAN diagram. So this is over 2 in the reals and up 3 in the imaginaries. Okay. Or if I give you an R-GAN diagram, I want you to be able to tell me what the imaginary and real parts are. I want you to be able to tell me what that is, what my radius is, and what my theta is. Okay, that kind of stuff. That goes back to our vector work a million years ago. Okay. It's not going to be too bad, but it's not going to tickle. So, I mean, as far as my tests go, it's not going to be the worst, but there will be some questions on there that you'll have to think about. How much time do you want to take for it? Well, yeah, I was gonna say the whole class. Do we want any more time?
I think 70 minutes should be good.
Well, that's 90 minutes, so I mean, I can give you the whole 90. Okay. Does anybody want more time?
I'm not gonna feel like doing it after 1:45 anyway.
Oh, poor Rick. 90 minutes it is.